All right, so welcome everyone back to 161, Fundamentals of AI. This is our lecture 4. And today we will be continuing with our discussion of problem solving using search. What we did last time is discuss the big picture, which we will review again next. And we focused mostly on how do we formulate problems as search problems by providing a specific set of components. And we did talk about the notion of search strategies, which you will have to use to solve these problems. And today we will start our discussion of search strategies. And as I said, there's 2 sets of them. So we will start with the first set today. So again, the lecture today will all be on the whiteboard. So as usual, I will turn my camera off next and then head to the whiteboard so we can start with our discussion. All right, so if you recall from last time, the big picture looked something like this, that we do have some kind of a problem. And we said that we can formulate it as what we would call a search problem, which demanded 3 ingredients, what we call the initial state, and 2 is the final state, and 3, the notion of actions that transition us between state. And we even said that this is something that can be specified using what we call the successor function, which is an abstraction, useful abstraction. And then we said that we pass this to what we call a search engine. And then we get a solution. The missing piece was, how does the search engine do its work? And there we said, you can pass what we would call a search strategy. And we did mention 2 types or classes of search strategies, what we called a blind or uninformed. And then the other class is heuristic or informed search strategies. And if you recall, the overall picture was that these are more powerful. These guys more powerful. They're smarter, but they do require more information. So these 3 ingredients that we mentioned are not sufficient for these guys. They would require a 4th ingredient, which we called a heuristic. We didn't discuss. Okay, so we're going to get to these later. Today, what we will do is we will talk about blind or uninformed search strategies, which are happy enough to do their work given only these 3 ingredients. And what we'll start with is a setting of the game before we introduce these guys. And let me just say one thing based on discussions I had with some of you after last lecture. So we did talk a little bit about search last time, or the search process, but in a very loose way, just to help you visualize what's going on and to explain the role of the initial state, final state, and actions, and why a search engine would need these. But we really didn't say much about how this guy works. And some of you had some doubts about what's going on there. So hopefully all of this will be clarified today. Last time we didn't talk really about what's going on here, only barely enough to motivate these guys. Today we will. Now, to talk about search strategies, we have first to explain something very important about the search process. So now we're going on here. Let me erase. We want to talk about the search process more generally which allows us to say something specific about what makes these search strategies different from each other. Because you will see, even though we're going to talk about half a dozen of them, what sets them apart is something very specific and very sharp and simple. All right, so we're going to do this first. So as I explain this search process, I would be introducing some terminology, which will be very important. And I'm going to put here a list of them as we go on, because you need to be quite precise on terminology and about what's going on. And that's pretty important. So let's say you give me an initial state, you give me a final state or a test of a final state, and you give me your successor function. And now we're gonna go ahead, okay, start the search process. So how does search work? The very first thing you do is you're gonna have your initial state. And that's the only thing that you have at this point. Now, you start by saying, well, let me check, is this the final state? If it's the final state, we're done. If not, then what happens? You go ahead and generate the children of this node by applying the successor function. So now we have the situation. Let's go ahead and do this. And I'm actually gonna start numbering these guys. Let's say 1, 2, 3. So this is how it looks now. What's next? What's next is I have to go and check whether one of these guys is the final state or goal state or not. So let me say I pick this guy. If it is, I'm done, and that's the solution. If it's not, so I go ahead and generate its children. And let's say there's 4 of these, and let's go and mark them 4, 5, 6, 7. Okay, now I've been using the terminology without highlighting it. So from there on, now I'm going to be a bit specific about the terminology that I just used. There is a very specific use of terms here. The first thing is these guys, 4, 5, 6, 7, 2, 3, that I have not yet checked for goal ship. These guys are called the fringe or the frontier. Okay, so at this point I have 1, 2, 3, 4, 5, 6 of them. Now, the other important term is, what am I going to do next? We talked about, oh, let's pick one of them. And let's say in this case, we picked 2. Look what happened here. Here, we have to be very precise. When I picked 2, I did 2 things. I'm going to do things. First, I'm going to check if it is a goal. If it is, or final state, if it is, I'm done. If not, I'm going to go ahead and generate its children. Okay, the term that I want you to pay attention to is generate. Okay, this is a very specific term, generate its children. So let's do that. So I picked this guy. I checked if it's the final state. It's not. So I'm going to go ahead and generate its children. So let's say there's 2 of them, and let's call them 8 and 9. Okay. These 2 steps that I did, check if it's the final state, if it's not, generate its children. Those 2 steps are called expanding the node. And that's another important term that I want you to pay attention to. Expanding the node. Okay, so let me highlight this. And if we want to go by what we did here, expand node versus generate children. Okay. These are important distinctions, and I'll tell you why in just a second. So, but let's just go ahead and do this one more step while using our terminology. So, guys, how many nodes do I have on the fringe at this point? I want a number. Just type a number. How many nodes do I have on the fringe? Okay, someone said 6, a couple of people said 7, and I'm getting more 7. Good, it is 7. It is this guy, 1, 2, 3, 4, 5, 6, 7. Okay, now we're going to use our terminology. If I complete the sentence, let's do this. Complete the sentence. Nodes on the fringe are waiting to be, and I want you to put in a word here. Nodes on the fringe are waiting to be what? Expanded. Thank you, guys. Expanded. Very important. Are waiting to be expanded. So I have 7 nodes that are candidates for expansion. And now I'm going to pick one of them. And let me say I picked 8. So let's again remember, what does it mean to expand 8? First, check if it is the final state. If it is, we're done. That would be the path, the solution. If not, I do what to its children? Type a word. I did the first step, it failed. I'm going to the second step, I'm going to generate the children. Okay, now I'm going to make one last observation and we're going to be done with this picture. The last observation is, if you look at what happened here, let's call this 1011. If we look at what's going on with this search process, there is only one decision that has to be made. And aside from this decision, everything else in this search process is fixed. So what distinguishes one algorithm from another algorithm is one choice. And I want you to help me phrase that. So now we can say one sentence that characterizes what a search strategy is. All right, so can someone type a sentence that tells me what decision characterizes, or what decision process characterizes a search strategy? Right? So I'm gonna write here and you complete the sentence. A search strategy is a criteria for deciding which, okay, fill in the blank. And okay, let's see. I see a bunch of you talk. Order of choosing nodes to expand. Fantastic. I'm reading the very first answer. Okay, someone said depth first versus breadth first. Those are the names of search strategies. But the answer is, some of you wrote order of choosing nodes to expand. Which fringe nodes to expand first? Absolutely. That's it. So a search strategy is a criteria for deciding which node on the fringe to expand next. That's it. The minute you tell me what is the criteria that I am using to decide which node on the fringe to expand next, then I'm done. I have a search strategy and I can tell you exactly what's going to happen in the search process. Pretty simple. Okay, it's very important. This is, I go over this very slowly, because if you understand this, these different search strategies will become very easy to navigate. Now, believe it or not, even though this is something very simple here, you can generate so many search strategies, and we will look at about half a dozen. Today, we will talk about 4 of them. In fact, 3.5. Well, three of them are of real interest. One of them would be just to motivate the last one. So it's more like 3.5 search strategies. And the only difference between them is this, how they make decisions on what to expand next. And you'll see the dramatic impact that that has. Okay, so remember, fringe, expand versus generate, and what is the essence of search is a criteria for deciding what now to expand next. Very good. Okay, we need to settle one more thing before we move on. And you're gonna say, wait a minute, you talk about half a dozen search strategies, and today we're going to talk about 4 of them. Really, what sets these things apart? Well, we're going to be very specific about how to set these things apart. We will have 4 different criteria to evaluate them on. So I'm going to go over these criteria next. And the idea is every time we're going to introduce search strategy, we're going to say, how does it rank on these 4 criteria? And you're going to help me with that. So we're going to say enough about the search strategies so that you hopefully can conclude what is, the rank, or how does that particular search strategy rank on these particular criteria. Okay, so here I'm going to write evaluating search strategies, and I'm going to write them. They're important. And by the way, what we're talking about today is a classical for a midterm, and I'll be a little bit more specific as we go on, but this is going to be on the midterm. This is so foundational. So there are 4 criteria that we're going to look at. And the first one of them is, I'm going to write the names and then we'll explain what they are. The first one of them is completeness. And the second one is time complexity. And the third one is space complexity. And the last one is optimality. All right, so every search strategy we're going to look at, we're going to say, is it complete or not? What's the time complexity? What's the space complexity? Is it optimal or not? And let me just be clear. So 2 of these are probably obvious to you, time complexity and space complexity. You know what that is, but we have to be clear on what is complete. And completeness here means, does it always find a solution if one exists? All right? Does it always find a solution if one exists? So we will see some search strategies are complete. They guarantee you, they will give you a solution if there is one. And some others do not. They may fail, right? So there may be a solution and they may go on forever and not come back. And they're going to say, wait a minute, so how is that useful? We'll see. Time complexity is basically, we're going to measure it by the number of nodes that are generated or expanded. And the space complexity, it's going to be specifically the maximum number of nodes, the maximum number of nodes that we may have in memory. And the last one is the one that confuses people, optimality. And I alluded to this last time. When you talk about optimality, it's a little bit ambiguous. What do we mean by optimal? Optimality may refer to time and space complexity. Is this the best you can do as far as time and space? Like, is it really efficient and you can do better than this? No, that's not what we're talking about here. Optimality is what we talked about, is optimality of the solutions that it does find. So this basically means, does it always find a least cost solution? Yeah, not the, because there may be multiple least cost solution, a least cost solution. Okay, I hope this is clear now. Optimality is, does it always find a least cost solution? And by the way, for today's discussion, the cost of an action is 1. We mentioned that you may have arbitrary cost of action, but today the cost of an action is gonna be 1. Okay, So I hope this is clear. Everything we're going to do, we're going to rank on these 4 criteria. Now, there's one couple of more things we need to do before we launch our discussion on the first search strategy, which is when specifying time and space complexity, these guys, remember, when you do time and space complexity, you have to say in terms of what. So if you're sorting, for example, then you would say, oh, the space complexity is n log n. So n here is the number of items you're sorting. So you need a parameter that represents the size of the problem so that you use it to express your time and space complexity. So again, sorting is very simple. N is the number of things you're sorting. What about here? If I'm gonna express time and space complexity, I need to basically decide on the parameters that I'm gonna use to express these complexities. So I'm gonna say time and space complexity are expressed in terms, and I want you to help me out here. And just to help you out, I need, so sorting is just one thing, n. Now here is going to be a little bit more involved. In fact, we're going to have 3 parameters that we're going to be using to specify a time and space complexity. And I want you to help me out with these guys. And we're going to give them names because we're going to use them systematically. So what are the parameters that we're going to use to express time and space complexity? And these are parameters that describe somewhat the problem. Any guesses? Someone said the size of the state space. So that means the total number of states. Not really, perhaps could be, but I need something a little more specific. Okay, someone said branching factor. And yes, this is going to be one of them. I'm going to put it as B. So we're going to use B for that. And that will be basically the branching factor. That's going to be one of the parameters that we're going to use to express time and space complexity. So I need something else. The depth of a solution, fantastic, yes. And we're going to use D for that. So D will be, okay. Now, I need you to be a little bit more specific here. You say the depth of a solution. Now, there may be multiple solutions. And okay, depth of the optimal solution. Thank you. So depth of the least cost solution. Okay, there is one more guy. There is one more guy. Okay, now this is perhaps a bit subtle. Oh, actually, someone already wrote something. Said, is this the depth of the optimal solution, or is it the maximum depth of the tree? Very good. Actually, we need both. And you just answered quite my question. This last guy will be just that, will be M, which is the maximum depth of the depth of search tree. Now, this guy, as we know, could be infinite. Right? Depends on the problem, but this is maybe infinite, depending on how we generate the search tree. Very good. So these are the 3 parameters that we're going to use, and we're going to introduce one more later for something more specific about what's going on. Okay, I need to do one last thing. And we're ready to go, which is an observation about the trees that will help us express time and space complexity. But someone is saying, why is it the least cost solution? Is it because we want to stop our expansion once we find? Yes, in a sense, right? The least cost solution is a more, think about it this way. And we mentioned this last time. So if I give you a problem and I tell you, look, the no solution can be done in less than 23 actions, okay? So, and then I give you another problem and say, oh, actually, this problem, you cannot solve it with less than 50 actions. So what does that mean? That means I have to really go as deep as 50. Otherwise, I can't find a solution. The first one, I can do it by going to depth 23 in principle. So that's obviously an important parameter of how difficult the problem is. Okay, so that's it. Okay, guys, one more and last thing, which is pretty important, and you should know this not just for this discussion, but more broadly. We'll put this under the label of an observation on trees. And basically what we need to do is to be able to count the number of nodes in a tree. So let's look at the following two concrete examples, and I want you to help me out. So let me look at a tree where the branching factor is 2. And let's say we're gonna keep going. And let me do one more level here. So let's do this, okay? Now, the first thing I need to clarify is the depth, the notion of depth. So what's happening here is this is depth 0. And this is depth 1, right? And this is depth 2, and this is depth 3. Okay, be clear on this. The root node has depth 0. And in this case, the branching factor is 2, right? So this is B2. And we're assuming a uniform branching factor. In general, as you know, the branching factor is not uniform. For some nodes, you may have 3 children. For another, you may have 7. That depends on what actions are applicable to that state and so on. But we're talking about the maximum branching factor. And for this analysis now, we're going to assume that we have a uniform branching factor. The thing that I'm going to end up with is, what is a formula for the number of nodes in a tree that is built uniformly like this, that basically have a branching factor of B at depth of D? We need like a closed form for this because it's important for our time and space complexity. And to help you maybe come up with this or understand at least what we're doing, let me just do another concrete example with a branching factor of 3, but I'm just gonna do 2 levels here so that it's not too heavy. Okay, that's what's going on. And in this case, the branching factor is 3. So the bottom line is this. Let's count. Let's start here. And hopefully you can give me the pattern. So I'm going to count level by level. Here I have 1 node. And here I have 2 nodes. And here I have 4. And here I have 8. And I have to add them. Right? That's what we want to do. I want to add 8, 4, 2, and 1. And that would be this guy here. And there's a pattern, but let's just try to do it here. Here there is 1, and here's there 3, and here's there is 9. So what is the number of nodes at each level? I hope you can see the pattern now. The pattern is what you have at a particular level. Here is 2 to the 0, and this was 2 to the 1, 2 to the 2, and this is 2 to the 3. And if you look at here, this is 3 to the 0, 3 to the 1, 3 to the 2, and 2 here is the depth. All right, so I hope you see it. So basically what's happening in this particular case is that if I really want to add these guys, so then what I'm doing is I'm adding 1, which is B to the 0, and then I'm adding B squared, and then, I'm adding first 1, then B squared, and all the way to B to the B. The question is, what's the closed form for this? And all the technique, I think one of the genius mathematicians did this when he was like a kid. That's the anecdote goes that way. You multiply this by B, and then you basically get B plus B squared plus B cubed all the way. Now you're going to get B to the D here plus B to the D plus 1, and then you subtract. So if you subtract, you take this guy and subtract this from it, you know, a lot of things cancel in this case, right? So when you just, you know, subtracting this from that, and so on. So you end up getting, at the end, if you do this abstraction, you basically get b to the d plus 1 minus 1. If you move things around, you're going to get the following closed form for this guy. B to the d plus 1 minus 1 over d minus 1. This is the formula we're after, but we're actually going to try to simplify it. We're going to say this is roughly the same as b to the d plus 1 over b minus 1. This is basically for large d. So sometimes we're going to use this. And in fact, we're going to even just write this as big O of d to the d. Now, in your book, sometimes you'd see d plus 1. We're not going to distinguish between d plus 1 and d. So that's what we're really after. Okay, remember this. So if you have a tree like this with a uniform branching factor of b, and you're generating all nodes up to level b, that's basically the number of nodes that you have. Okay, very good. We're almost ready to go to our first search strategy. And I just want to also make one more observation here. And you'll find it actually pretty important later, because there's something we're going to do later which is going to be very surprising. And if you see what I'm going to mention next, you will realize that it shouldn't be surprising. Look at this tree. How many nodes are on the last level? 8. Okay. How many nodes are on level 1, 2, and 3? Everything but the last level. Count them. How many? So the very last level had 8 nodes. Every other level, when you add them up all together, what do you get? You get 7, right? So 1, 2, that's 3, and 4, 7. This number is greater. So I have in the last level as roughly as many nodes I had over every other level. So the last level, or the nodes of the last level, dominate. Now it gets worse as the branching factor increases. Look here. How many do I have at the last level? 9. And the first and second is only 4. If you expand further, it gets even worse. You're going to find that the nodes you can have at the last level is significantly larger than the nodes that you had on every other level. So bookmark this observation, and we're going to come back to it later. Okay, guys, I think we've had enough of preparation for going to our first search strategy. So let's go ahead and do it. And the first search strategy that we're going to start with is going to be depth first search. Now, again, let me say something here before we go on. Some of you say, oh, I know depth first search. I know breadth first search. This is simple. This is boring. No, let's listen in. Okay, if you've heard about these in your algorithms course, we're going to just provide a little bit of a different perspective here. So pay attention. And again, almost every midterm has a question about these, and I'll tell you particularly what the question will be as we move on. So here's the game, and we're going to do it for all of the 4 strategies that we're going to be doing today. I'm going to show you. Let me see first. Let me just write the title: Depth First Search. So this is our first strategy, our first search strategy. So we're going to have this tree. That is, I'm gonna lay it out here. The search algorithm is not gonna see what I'm putting here, but what this shows you effectively is the nodes and their children. So that defines the initial state, final state, and the successor function. Again, the search algorithm does not see what I'm showing you here, but it is for us to simulate the search algorithm. So here we have HI and JK. You're going to give them numbers, LM and NO. Okay, that's initial state. This is, let's say, this initial state, and I'm going to make this the final state. Oh, this last guy here. So that's basically defines the search problem: initial state, final state, and the successor function. So what we're going to do is we're going to look at a search strategy from 3 angles. And the first one is going to be a bit tedious, but it will show us something very important. All right, so we're going to go simulate. And well, I have to tell you what depth first search is first so that we can simulate it. Because the reason we want to simulate it on this problem is hopefully by the time I finish and I ask you the 4th question, what is the time complexity? What is the space complexity? Is it optimal? Is it complete? You're going to tell me the answer. I'm doing it in enough detail so that you can infer the answer for these 4 questions, which is important because we want to modify what we're going to be doing next. Okay, I screwed up here. We are not doing depth first search first. We're doing breadth first search first. Okay, so let me go ahead and do this. And while I'm typing this, remember, what did we say about a search strategy? It is completely defined by the criteria that is used to decide which nodes to pick from the fringe to expand next. So what is that criteria? First, we have to specify that criteria, and then we go and simulate. So what is that? Can someone guess from the name or because you've had exposure to this before? What is the criteria that we're going to use to expand? If you have choices on the fringe, which one do you pick? Give me criteria. Okay, I presume many people have heard of breadth first search in some context. Okay, someone says, choose fringe nodes on the same level. Someone said arbitrary. No, if arbitrary, then I don't have a search strategy. I need a specific choice. If I have a fringe that has a whole bunch of nodes waiting to be expanded, I need a criteria on which one to pick to expand next. The one that was on the fringe first, the node with the highest height. Okay, now we're starting to get in business here. I'm not there yet. Breadth first search. Okay, good. So I hope this illustrates something, that even though a whole bunch of you have heard about breadth first search, apparently you don't understand it enough to the level that you will understand it after this discussion. Otherwise, you would have crystallized what is this criteria. The criteria is the following. We're gonna pick the shallowest node first. Okay. Now, remember, every node that is sitting on the fringe has a height or has a depth, correct? Because it's part of a path. It's coming from the root initial state all the way to that guy. So it has a certain depth. How many steps did it take me to get to it? And what breadth first search does is always picks the shallowest node, the one with the smallest depth, to basically expand next. Now, of course, you may have ties, then it doesn't matter, but that's the criteria. Okay, and let's go ahead and do this, and let's see how much time we have. We started a bit late, so I want to actually do this segment, and then we can take our break after that, so that we don't interrupt the flow, given that we are at this particular point. Okay, folks, here's what's going on. Let's go ahead and do this, and it's going to look a little bit tedious, but it's important. So I'm going to start by having only this guy on the fringe. That's basically it. That's my first fringe. And then you're going to help me here with the words. So the fringe has only one node. I'm going to pick a node from the fringe to do what? To expand. So what does that mean? Check it. Is it the goal? It's not the goal, because that's my goal. So what do I do in this case? I go and generate the children. So now this is how it looks. This is how the working space looks like. I generated the children of A. Now, the fringe now has how many nodes at this point? The fringe. This 2, B and C. I have to pick one of them. Breadth first search says pick the shallowest node. This has depth 1, depth 1. Both are equally good, but I'm going to go ahead and pick B. I'm going to break a tie this way. So now I'm going to generate its children, and now this is how it looks. Okay. Now the fringe now has how many nodes at this particular point? How many? 3. 3. It's B, E, and C. Okay, I'll have to pick one of the 3 to expand next. Which one, according to breadth first search? C. I have no choice. Why? The depth of this is 1, 2. The depth of this is 1, 2. D and E have depth 2. This has depth 1. Choose shallowest node first. It has to be this guy. I don't have a choice in this case. So I'm going to go and do this. And it happens not to be a final state. So I go ahead and generate the children. And now this is how things are looking. So I have DE, and now I have FG, and okay. How many nodes do I have at the fringe at this point? There's 4 of them. This guy, this guy, this guy, that guy. Which one do I choose according to a breadth first search, or what is also known as BFS, breadth first search? Now, which one of these 4 do I choose in this particular case? Any of them, fantastic. Okay, someone said D. No, any of them, because they're all at the same depth. BFS, the breadth first search, cannot distinguish between them. It says pick any that you want. Okay, you know what's going on. I'm just gonna roll this for a couple of steps, hopefully up to the point where you're ready to make the inferences that we need to make. So if I go to the next step here, let me see, it's gonna look like this. I'm gonna pick this guy. I will pick D to expand next, but that's an arbitrary choice. It could have been any of them. So this is HI. And let me go and do this guy again. So now I have FG, I have DE here. Okay, HI. Now, the next thing, any 1, 2, 3, 4, 5 on the fringe, I can pick any of these 3. Let me say I pick this guy. So it's going to be JK. Okay, you see what's going on here. So da. And at some point, I'm missing a couple of steps. You're going to get to the point where you have the following situation in memory. All right. We have basically D, E, and F, and G. Da. Okay. And then basically H, I, J, K, and L, M, and O. That's, I'm going to get to this point. And at this point, what is the fringe? The fringe is all of these guys, 1, 2, 3, 4, 5, 6, 7, 8. I can pick any of them. Of course, I can make this painful by saying, let's pick H, I, and then we keep going. But actually, I will eventually going to look at this guy and you find your goal. So it keeps going. But the point is, I wanted to show you that we got to this point. So here's what we're going to do. We're going to take our break, but when we come back, we're going to do a few things to finish this story. And let me write them here for you so that you can get prepared for them. One of them is I want to go to this tree and order the nodes according to the order in which they will be expanded by breadth first search. That's a very important thing. We're going to do this for every strategy we're going to look at. Or number them according to the order in which they would be expanded by particular search strategies, because that numbering is going to tell you a lot about this algorithm. We're going to do this number nodes according to expansion order, and you can basically think about this. The other thing we're going to do is implementing breadth first search, an observation about this. Okay, so this would be an observation, which would be interesting. But the last thing we're going to do is rank breadth first search across the 4 criteria that we talked about. All right, guys, so let's take a break. Let's see, what are we doing here? Let's get back at 11. and finish this story off so we can move to the other guys. All right, guys, I'll see you at 11. All right, folks, so we'll keep going with the next part of the discussion, and we're getting to the punchline here. So I'm gonna do a couple of more things, and then I want to answer the 4 questions for me, all right? So let's go ahead and do that. The first thing we're gonna do is the number the nodes according to the expansion order. So help me out here. I'm gonna go put those numbers in blue. We're gonna do it on this guy. What I wanna do is I'm gonna go say 1, 2, 3. I give you the number, and I hope you can type in the node that will be expanded in this order. So I'm going to help you out. I'm going to start with the first guy. This is the first guy that will be expanded. So that gets the number 1. Now, help me out here is who gets number 2, who gets expanded next according to this. And you realize here that there would be ties, but maybe do them just like alphabetically. So break the ties alphabetically, okay? So if there's a tie, alphabetically. So someone said B or C, so it will be B. So let's do this. 2. Who gets number 3? Okay, people are saying C. And by the way, this notion of here's a search tree, the full search tree, and number the nodes according to the order in which they're expanded according to strategy X, it will be open. So that you know. Okay, so who gets 4? I need 4. D. Very good. 5. Who gets 5? 5. People are typing E. Good, good. Who gets 6? People are saying F. Who gets 7? Okay. Interesting. So you can see what's happening now. So then 8 will be, I'm pointing to it, I'm cheating here, so I'm giving you a hint. 8 will be, which would be 8? Which node will be 8? And people are saying that. So it will be 8, 9, 10, 11, 12, 13, 14, 15. Okay. I hope you see the significance of what we did here by numbering these nodes. Okay, so look what's going on. Let's do this. You're doing 1, 2, 3, 4, 5, 6, 7, 8, 9, dot, dot, dot. So if you had more, then it will be dot, 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 dot. Okay, remember this, because it's going to be the secret for answering the 4 questions that we're going to be talking about, or at least some of them we're going to be talking about next. Okay, we're done with this guy. Let's do the second guy. The main observation about implementing breadth first search is the following. If you maintain the fringe as a queue, then you will get this. So what you can do is you can start by having, the node A on the fringe. And remember what the queue is. A queue is you put nodes on one side. So in this case, when we generate children, we're going to put them on this side. And when we expand, we're going to pull from the other side. All right. So this is expand. We pick from this side, but generate children, we add them here. Okay. So if we do this, look what happens. You start with this guy, then you're going to expand it. So you add its children. So those are BC. Okay. Still not interesting at this point. So now the next thing is, and I'm going to use me for this. I'm going to expand. Which one do I pick? This guy, because it's on this side. So I remove this. And now what are the children? DE. But where do I put them? I put them on the other side. So now I have basically C and I put DE on this side. And I just repeat the process. So the next thing to expand, I pull from this side. So it's going to be C. And when I remove this, and it's not the goal, I add its children. The children is F and G. I put them on the other side. E, F, G. And you can keep going with this, all right? So if you use a queue to maintain the fringe, you get the behavior that you want, which is you're going shallowest first. All right. Folks, we're getting to the punchline, and now it's your job to do the next step, because I hope I gave you enough information where it would be easy to answer the upcoming questions. And the upcoming questions is just like what we are going to do for every one of them. let me go and put a green box here, which is going to be the guy where we're going to put the answers to the 4 questions. And here we're going to say evaluating breadth first search and the search strategies. And we're going to look at the 4 questions we looked at. 1, 2, 3, 4, and you're going to fill this for me. All right. The very first question, complete. I'm going to put here complete, and then you're going to be answering. This is optimal. And that's the question. And this is time complexity. And this is space complexity. All right, guys, help me out here. First question is complete. Now, remember what complete is. Complete means if there is a solution, the algorithm is guaranteed to find it. It's not going to go into an infinite. Right? So if there is a solution, it will guarantee it. It will not miss it. And the question that I have for you is breadth first search complete or not? So you have to say yes or no. You have to say yes or no in this particular case. Okay, a lot of you are saying yes. I don't know if it's a lot, maybe a dozen. I was hoping for a little bit more, but yes. And the reason why that is the case is, as you can imagine, because of the systematic fashion in which breadth first search examines things. It goes level by level. So it goes level 0 or depth 0, and then it expands every node at depth 1. And then it expands every node at depth 2. And here's the way to phrase it. And this is important. Let me put it this way, and this should be obvious from the expansion order. Breadth first search. Okay, I have to dramatize this. To dramatize this, I have to turn the camera on. The breadth first search will not expand a node at a particular level before having expanded nodes at the previous levels. It will not touch something at level 17 before it has checked level 16 and above. Okay, now I turn the camera off. This is important, and this is going to be the secret for the last one. What about the optimal? Is it optimal or not? After everything I said, you gotta get this answer. Is it optimal or not? Yes, it's optimal. And why? For the exact reason I just mentioned. The way you end up being not optimal is you end up expanding a node that is a solution. So you stop, say, I found a solution. Even though there is another solution that is better. This cannot happen in this case. Okay, and remember, we're assuming here that every action costs 1. So indeed, it is optimal for the exact reason that I mentioned. Now, what about time and space complexity? Let's start with space. What do you think is the space complexity in this case? And I gave it away for you. B to the D, right? Because you saw what happens here in the worst case. In the worst case, I end up having the whole tree in memory. There's a reason why I did this for you. All right. And what about the time complexity? What about the time complexity? Okay, silence. Okay, here's the thing. And I get an answer that it's B to the D. Folks, here's an observation. In the hindsight, it's obvious, but we miss it all the time. If you had to go and store a certain number of things in memory, you have to do work. You cannot, your time cannot be better than your space in this case, right? Because if you're going to go put a node in memory, you work that much, all right? So in this case, the time complexity is always less. I hope you got this observation, right? If you're adding this to memory, you've done that much work. So you cannot be doing less work than the space you created here. So that's okay. Well, let's see. How is the news on breadth first search? 1 and 4 looks really good. 2 and 3 are really bad, particularly this guy. space, right? Sometimes people can wait, things are faster. Okay, now we go to the next guy. The next guy, and here's what's going to happen. And just to give you a sense, so we do have enough time to finish the story today. And let me do this. I hope I can turn the camera on and off in a more seamless way. Folks, what's going to happen is we're going to do the next guy, which is guess what? Depth first search. And we're going to see that it will rank a little bit differently. And we're going to see that breadth first and depth first, each one of them has good things and bad things. So none of them really completely wins. And then we're going to make a fundamental observation. And then we're going to give you something that actually end up being the best of each, which is almost like a miracle. And it's a very fundamental and cool observation. And I hope you will discover it yourself. And then we'll end up with a trophy for today, which is a particular algorithm. I can't tell you what its name is, because if I tell you the name, I'll give away the idea behind it. So there is a big punchline coming up here, but let's go ahead and do depth first search next using the same style. Hopefully we'll do it faster now that we understand the game. All right, back to the whiteboard. So here's what's going on. And this guy is depth first search. Okay. I'm sorry, I have to. Let's say depth first search. Okay, it's going to be a little bit, again, tedious in some sense, but bear with me, guys. I have to switch notes here. So we're going to look at the exact same thing. We're going to look at this tree here. I'm going to try to do it fast. And here I have the E. So I couldn't preserve what I wrote because of all of the numberings. So we have to do this. Now, as I'm typing or as I'm writing, remember we wrote something here for breadth first search, which is like a single line that told us what is the criteria to use. So as I'm finishing this off, I want you to type something similar. You're going to make a guess based on the name of how will it choose nodes from the fringe to expand next, right? So you guys make a guess. You're experts now. You should be able to do this. So depth first node. Okay, so someone said deepest node first. Exactly. So expand deepest instead of shallowest node first. That's the one-liner characterization of what this strategy does. And here we're going to do it. And let's go and run through this. And again, same story. I'm going to roll this, simulating it. And hopefully, from the evolving picture, you can predict the properties, because that's really the main thing we need to do. So I'm going to start with this as usual. It's not the goal state. So I expanded it. Then I'm going to go and generate the children. And now I have BC. Now, the fringe now has BC. I can have to decide which one to choose. They both have the same depth. Doesn't matter. So let me pick B, because we're doing breaking ties alphabetically. So the next step, it's going to look like this. And now my fringe has these three nodes, this, and then I have to pick one of the three. So here's the question for you. Which one do I pick? According to depth first search, which one? Okay, someone said D. So a better answer is D or E, right? Because they're equally good and we're breaking ties alphabetically. So look what's going to happen next. And just soon enough, you're going to see how the picture is going to start looking very different from what happened in breadth first search. So here I have H and I. Aha! Okay, quickly, how many nodes on the fringe? Number, give me a number. How many nodes on the fringe? 4. How many of them, which one should we pick next according to the first search? Which one in this particular case? Okay, people are saying H or I, fantastic. Okay, now I'm gonna pick H and look what's gonna happen. Now we didn't see what's gonna come up next. We didn't see it in breadth first search because we didn't roll it enough, but look what's gonna happen here. I pick H. H is not a goal. So what happens? Then I'm gonna basically generate its children. It has no children, so it just goes away. And look what the picture looks like now. The picture looks like this. Right? That's how the picture looks like. Now, at this point, I have 3 nodes on the fringe, this, and that. There is no choice for depth first search. It has to do this one, okay? Because that's the deepest. Now, look what happens. You pick I, it's not a goal state. I want to generate the children. It has no children. Now, when I take it out, D will also go away because there is no reason to have this anymore. It was just there to lead me to the, so now I have the picture that looks like this. That's how it looks now. All right. And again, at this point, the 2 nodes on the fringe, this and that, I have no choice. I have to pick this guy. So it ends up being BC, and then I have the E, and then I have the 2 children, JK. Okay, I hope you see now what's going on. Okay, let's do this. I'm gonna roll this for you because it's pretty important again to see what happened. So the next step is I pick J. It's not a goal state, there is no children. So I end up being in this particular situation. And then I have K. Okay, look, here's what happens. Something dramatic is gonna happen. Next thing, again, I have no choice. 2 nodes on the fringe, C and K. I have to pick K. I pick K, it's not a goal, no children, it goes away. This has to go away, this has to go away. And now it's looking like this. There's only 1 node on the fringe. And then you just keep going. So now you're gonna have this, you're gonna have this, you're gonna have FG, and dot, dot, dot. Let me just, okay. I'm gonna do 1 more, and I'm gonna skip all the way to the end. So this is gonna look like this, and this is FG, and this is gonna be LM. Okay, guys, dot, 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 but let me show you how it's gonna look at the very end. Anybody wants to guess what's gonna happen at the very end? Type a word. There is a word that probably describes the picture at the very end. Okay, someone really, okay, guys, you're good. Okay, so it's gonna look like this. I'm gonna have O, no, what is O? There's no O. Okay, it's like C and G and oh, fantastic, absolutely brilliant, guys. And I get lucky now. I pick this guy and I'm done. Okay, guys. Okay, let's do the 2 exercises. Well, first, let me say on implementation, when we did breadth first search, we maintained the fringe as a queue where we expand nodes from one end, but we generate children, we add them to the other end. Just make a wild guess of what would be the data structure for the fringe to get this behavior. Okay, just type something, stack, yes. And you can play around at home with that. So you put children when you generate them on one side and you pick them from that side as well when you want to expand. But let's do the other 2 things so that we can go to the cool stuff after that. What happens next? What happens is, as we did before, right? So first we said we order according to expansion, and we basically did the implementation node, and then rank or evaluate. Okay, expansion. We're gonna play the same game, guys. So I'm gonna say number 1, and you tell me what. Okay, and break ties alphabetically. Let's do this in blue. Here we are. Number 1. I'm gonna help you with this one. It's gonna be this guy. Number 2. Number 2. In terms of expansion, give me a number, B. Okay, number 3. Number 3. Okay, people are saying B. Okay, number 4. H, fantastic. Okay, number 4. Now, number 5. Okay, you're getting it, guys. Okay, let's do a couple of more. 5. Now, what happens number 6? Number 6, and people are typing, there was J somewhere there. Okay, no, there's no J. It's gonna be this guy. And number 7, it's gonna be this. Number 8, this. Okay, number 9. Okay, this is number 9. Okay, let me play a trick with you. What's gonna get number 11? So that's less boring. We're skipping 10. What's gonna be number 11? Okay, what's number 11? Okay, you guys got it wrong. Some of you got it wrong. Okay, number 11. It's gonna be this guy. So it's like 9, 10, and then this is 11, and that's 12, and then 13, 14, and 15. Okay, that's not a cute 13. Let's change it. 13. Okay, you guys see what's going on? I want you to visualize it because this numbering is very important. What's gonna happen is, let me do it in green. You're gonna go like this. Here. Okay, see my hand. Then you go like this. Okay, and then you go back this way. Okay, and this way. And then all the way back here. And then this. And then this way, that way. Okay. That is not very pretty. Let me see if I can take it out. Okay, good. So you see what's going on, guys. Completely different behavior than breadth first search. So now the question that I have for you, are you okay, I think people are supporting each other. That's good. Now, folks, are you ready for the questions? Are you ready for these guys? We're gonna do these guys now. And you have to tell me what the answer is. You have to give me the answers to these questions. And do I have enough room to do that nice green box? We'll make room for it here. Let's squeeze as much as we can. I like to keep things on the basically the screen. And remember, so this is evaluating depth first search, and we have the 4 criteria: 1, 2, 3, and 4. And you are the one who's gonna tell me, optimal, is it complete? And then time, complexity, and space complexity. And I'm going to help you out here by reminding you of the parameters we used before. Remember what we did for the parameters to express space and time complexity. We had B, the branching factor, we had D, and we had M, which is the depth of the search tree. These were the parameters for the complexity. Okay, guys, help me out. First question, is it complete? Is it complete? Is it guaranteed to find an answer or solution if one exists? Okay. A lot of you are saying yes. Almost everybody. There's a guy that said depends. And someone said, wouldn't depth first have a problem if the maximum depth is infinite? Oh, whether the tree has a bounded max height. What if the tree is infinite? Okay, now we're talking. Yes, the tree could be infinite. The tree could be infinite. We did not talk about checking for repeated states. So in principle, you could be going into an infinite loop. And in some problems, you will not have repeated states, and another you will. So having said that, for all of these guys who typed yes, you want to change your answer, you can have a change of heart. Is it complete? Yes or no? Okay, it is not, right? Because of that reason. So it is not complete, no. And is it optimal? Is it optimal? Now remember, optimal means it will find the least costly solution. And I do have few that said no, not enough people. So there's a little bit of doubt. So guys, look what happened. Here's the picture. Here's the picture. Look what happened with the expansion. This is a finite tree. So here, it's going to be complete, right? So it's not an infinite tree. So it is complete. But look, what if this was the final state? Look what this guy will do. And let's say this was a final state as well. Now, this is not optimal, correct? And this is basically optimal. In fact, let's make it, yeah, we're gonna make this guy the final state. So what's gonna happen here is it's gonna go down keep going down, and it's going to hit this guy, and it says, got it, I found you a solution, but this guy is better. But it didn't, because it keeps going deeper. So okay, so someone said, so if we have an infinite tree, we may be going down the leftmost. Yes, possibly. Exactly. Okay, so I hope now you realize it's not optimal. Some of you said that, but more clearly. Let's finish this thing off, guys. Time and space complexity. Time and space complexity. What is the time and space complexity here? We need to move on, guys, so help me out. And let's start with space. Let's start with space. What do you think, space? What do you think is going on with space? Look at it. Well, for one thing, these trees look way skinnier than the ones we've seen with breadth first search, right? So, in fact, look at it. You can convince yourself, especially looking at this picture, that okay, no, this is not, let's use green. What's happening with these things is, look here, look here. I'm looking at the longest path. What's happening? This guy is the height of the tree and some additional nodes. So it is linear in the height. But as you go down, you may have to have siblings. And the number of siblings that any node of that tallest path, the number of siblings is no more than b, the branching factor. So in fact, in this particular case, the time complexity, the space complexity is going to be just bm. And m, not d. D is the depth of the solution. This is the depth here. But you may go down all that way. So it's b times m, which is the space complexity. And the time complexity is just like breadth first, because if this was your final state, right, then you see what's going to happen. Look at it. Look at the node orderings. 1, 2, 3, you have to do almost everything. You have to touch everything to get to this guy. So that's going to be b to the m in this particular case. Okay. I hope you realize this notion of ordering nodes according to expansion, how significant it is, because it tells you the whole story about the algorithm and allow you to infer its behavior. Okay, so quickly, before we get to the punchline, and we have 20 minutes, I think that should be enough for the last strategy. Compare this to breadth first. The news doesn't look good. So time complexity is the same, okay, in a sense, right? Where there is m here and d there, but let's just say both are exponential. The good news is what? So I have 1, 2, 3, 4. The good news for this compared to breadth first search is what? There's something substantial here compared to breadth first search, something significant. Space, okay, exponential to linear, that's very significant. That's this guy. Okay, now things look bad though on the complete and optimal side compared to the other guy. Yeah, but even it's right. So the problem is with these two guys, and so our last strategy will try to get the best of both of them. And then you see, wow, how can that happen? Well, we'll see. But to motivate this last strategy that we want, let me ask a question. There are some situations where you can modify depth first search a little bit and recover completeness. Let me give you the hint. Sometimes, depending on the problem that I have, and if I think a little bit about the problem, I can modify this guy so that it ends up being complete. Can you guess what that is? Or can you think of that? And okay, already somebody came up with an idea. The idea was, what if I limit the height? So I just don't go below a certain depth. I say, hey, depth first search, do your business, but please do not go below level 50. Okay, so don't go beyond 50. So now it's not infinite. Now, the question is, when I said I want it to become complete, will this make it complete? So if I limit the depth, if I say don't go below 50, now I know it's not going to run forever, but is it going to be complete? Is it guaranteed to return an answer or a solution if one exists? Someone says no. Why? Tyler, why? And you know, more people are saying no. Why? Okay, thank you. Someone said, what if the solution is at level 51? What if the optimal solution is at level 51 and you cut it off at 50? You're gonna miss it, you're not complete. Okay, now here's the thing. Sometimes for certain problems, you can say that my solution is not gonna be more than 50, right? You may think about it, about your problem, and find out that there must be a solution with less than 50 steps. So in that case, it is safe to cut it off at 50. And this algorithm is called limited depth search. Give me a second here, guys, or depth limited search, what we just did. And this is basically a variation on depth first search, where you basically effectively what you're doing is DFS with depth limit of L. Now, what happens here? The main thing that happens here is, well, a bunch of things. Optimal, is it optimal? Well, if D is basically less than or equal to L. Okay, remember, D is the depth of the optimal solution. So if I don't cut prematurely, then yes, it is optimal. Now, time, complexity, space complexity, and is it optimal? Okay, sorry, this is not up. This is complete. I messed up here. So is it complete? If D is less than or equal to L. Okay, and now the question is optimal. So quickly, guys, help me out. What is the time complexity in this case? What is the time complexity in this case? And the space complexity. We're cutting off at depth L. So good. People are saying now it becomes B to the L. And what about the space complexity? What about the space complexity? Now it becomes BL. Very good. And the last question, is it optimal? Is it guaranteed to find the best solution? Okay, I do have only one answer. I was hoping for more. Let me draw the picture for you. Here it is. Something like this. And this is, you know, and you say cut off here, right? So 1, 2, 3, L equals 3. And your solution could be here, right? And there could be another solution there. Okay. So people are saying, no, 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 I guess not. Right. So it is not optimal. It doesn't give me optimality, but it is safe completeness. Okay, guys, now we're going to get to the punchline. And we have about 15 minutes or so to finish this last story. So this guy is good. It's an improvement in a number of ways, but it requires this. Now, what is this? This means I have to think about the problem. It's not a domain-independent algorithm. It's an algorithm to get these nice thing of completeness. You will need to think about the problem and try to bound the size or the optimal solution or the cost of the optimal solution. Now, what if I don't want to do that? What if I don't know enough about my problem to really say you must have a solution less than or equal to L. But I still want to do something like this. What should I do? Something along the same lines, where, and in fact, it will even be better than this, because what happened here is if you compare this to breadth first search, look what happens to breadth first search. Breadth first search was complete, and I'm here, we'll get completeness under this. Okay, I made an improvement. This is better than breadth first search in terms of space. It's basically exponential time and it's worse. But the next thing we're going to do will make this domain independent, but will also generate a blast. Let me see what people wrote. Oh, well, someone gave me a name. I don't want a name. You already apparently know what's going on, but we do a small and then divide the full tree into chunks. So one solution I'm getting is we do a small L and then divide the full tree into chunks of L depth. Can we sharpen it a little bit more? Can we sharpen it a little more? In fact, let me do this. I want you to think about this. And as you're thinking about this, I'm going to go ahead and draw a picture for you. And hopefully this will tell us what's going on. So I'm going to go, and this next slide is going to be about the very last guy. I will not write the name. I will just do this, and we're going to add the name. But going to the problem that we already worked on, I'm going to draw a picture for you. I'm going to do this. And hopefully from the picture, you can infer what's going to happen. I'm going to do this. Okay, your job is to discover this technique based on the picture that I'm going to be drawing. Well, this picture will serve another purpose, by the way. All right, guys, fire your neurons. L, M, N, O. All right, I drew this picture. Let me see. Okay, someone wants to ask Professor Korf. He would be more than happy to be asked. And by the way, Korf actually made substantial contributions to this area. He's one of the world experts on this subject. Folks, here I drew a picture for you. Look, I mean, the trick with limited depth is basically coming up with this cutoff. I have two problems with the cutoff. If it's too small, I may get in trouble, right? So if I say cutoff at 15 and the best solution is at 18, I'm in trouble already. I don't even have completeness. So that's one problem. The other problem is if it's large, then I don't have optimality, right? So if let's say, if you know for sure that there is the best solution is at 18, I say cutoff at 18. So not only let me actually, so in that case, if you know that the optimal solution is at level 18 and I say cutoff at 18, not only do you get completeness, you get optimality as well, right? So you're going to get the best guy. You know, you're not going to catch something worse first. So how do I do it without knowing something about domain, getting this number? I can't, in a sense, I want to get it right. I don't want to have it smaller. I don't want to have it larger. Okay, we'll do like these shows where we're gonna dramatize a little bit and wait, because it's really a simple idea, and I just want you to have this moment of thinking about how could that ever happen, and then you see it and you say, next time when I see that something is impossible, I should think a little bit more because it's possible. Let's see. I don't have any solutions yet. Okay, I mean, obviously, this is something that's going to be so easy in the hindsight, but it's not easy to just see. Otherwise, people would have discovered it much earlier. Okay, are you ready? It's so simple. It will take like 2 sentences to explain the idea. Are you excited enough to hear it? I need, okay, good. At least I'm getting few saying yes. Okay, more people. Okay, turn the camera off and let's go to the whiteboard to explain the idea. Guys, here it is. Look, we're gonna say we'll do the limit business, but I'm gonna start by setting the limit to 0. What does that mean? That means cut off at 0. Says, are you kidding me? Yes, I'm just do it at 0. Now, what does it mean to cut off at 0? That means you're just gonna look at this and you're gonna expand it. And if it is the goal state, you're done. If it's not, right? You just say, I'm done because I cut off at 0, no solution. Now that's not correct, So if this succeeds, I'm good. If it fails, what do? I go and cut off at 1. All right, I go and cut off at 1. What does it mean to cut off at 1? That means you're doing this. So you're doing depth first on this. You're gonna check this, and then if not, you do this and you do that. Again, if you find a solution, you succeed, then good, done. If you fail, what do? You go try cut off at 2, and so on. This way, you're guaranteed the first time you have success, you're gonna have an optimal solution. Why? Because if there was a shorter solution, you would have found that earlier. Okay, so that's basically what the idea is. You start the cutoff at 0, and then you start incrementing it until you reach success. This is complete, right? Because you will not go, in a sense, to another level before you have examined things at the previous level. And it is optimal, right? Because you're going to be checking things at a particular level before you check things at the next level. Now, someone is writing, isn't this just turning it into a kind of breadth first search? Yes, except I maintain the linear complexity, this linear space complexity, absolutely, Kyle. Because look what's happening. I'm doing depth first on this guy. I'm doing depth first on this guy, and I'm doing depth first on this, and I'm doing depth first on that. I'm doing depth first on this. And so each one of them is taking linear time as far as space, but because I'm examining them with these increasing levels of cutoff, I'm getting the behavior and the properties of breadth first as far as completeness and optimality. So this algorithm will end up being complete, will end up being optimal, will end up having linear space complexity. And of course, we can't escape the exponential complexity in general. Now, someone's saying, interesting, so you start over from the root each time? Absolutely. And we're going to see this very clearly by numbering them, and you're going to help me with the numbering now. When we do the numbering, I just want to do one more thing because there's a catch, but I don't want to distract you yet. Folks, help me out here with the numbering. And remember, what we're doing, depth first on each one of these guys. And I can do this because by just setting the cutoff. So this is the cutoff of L equals 0, L equals 1, L equals 2, L equals 3. Okay, help me out. I'm going to number these. And so in blue, when I start here, okay, it's obvious. I visit this first. Now, when I do the second guy, I increase the depth. I'm again starting fresh. So this is going to be 2, 3, 4. All right. Now I go to the next level. I'm doing depth first on this. We know how to label depth first. So this would be 5, 6, 7, 8, 9, 10, 11. And then I have iteration, the 4th iteration. Then in that case, it's going to be 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I hope I did not make a mistake. Should be good. So look what happened here. If I were to tell you this in an exam, order things according to the expansion order by, okay, this algorithm, you want to make a guess what it's called? It is called Iterative Deepening. Okay, now iterative deepening. So if I tell you number nodes according to order of expansion by iterative deepening, look what's going to happen. And here's the tree. The full tree was BC. We do this, and we do D, E, F, G. Okay, let me just do the whole thing. Sorry, guys, but we need to see this so you can get it correctly on the exam and you understand what's going on. So if I give you this guy and I say number nodes according to the order of expansion by iterative deepening, so you're going to end up putting here the number 1, 2, 5, 12, and next to B you're going to have the numbers 3, 6, 13. You get it, guys? So this guy will be 4, 9, 20, and so on. I hope it's clear, right? Any questions? Is this clear what's going on here? So we're starting afresh. Now here's the catch. When you see this, and let me keep going. So in fact, let me just put the numbers. So this is going to be like 7 and 14. And now you're going to tell me, wait a minute, you told us this is going to be the best of everything. But there is a catch here. So what is the catch? I think this is going to be 10, 21. And this is going to be 11, 24. And finally, these guys are going to be 15, 16, 17, 18, 19. Did I get it right? No, I got it wrong. Let's just do this. So I think this was 50, 16, 18, 19, 22, 23, 25, 26. Okay. So remember, I hope you're convinced with the fact that this is basically optimal. We say yes. It is complete. And here we say yes. Time complexity and space complexity require maybe a little bit of more discussion. Why? Because there is this business of repetition, and people are saying time complexity is in the garbage here, but I guess space complexity is good. Well, okay, let's do space. For each snapshot that we have, it's linear space, obvious, correct? For each snapshot, it is linear space. And I'm not keeping space across the snapshots. Okay, so the space complexity is good, as people have observed, which is pretty nice. And in fact, in particular, the space complexity is BD. The space complexity is BD because I'm not going beyond D. Remember, clearly, when I'm increasing these levels of depth, L, I'm not going to go beyond D, the depth of the best solution. And so I have BD sorry, B multiplied by D as far as space, which is excellent, right? So this is really good. The question is the time complexity, and this is what people are concerned about, and some people are saying that it's already a problem. Actually, it is not. And I already told you something earlier, which gives this intuitively that you're not going to have trouble. I'll tell you intuitively, and then I have one last derivation quickly that I'm going to do to actually show you that the complexity here will end up being also b to the d, even though with these repetitions. And the bottom line is, remember when we talked about trees, we said that the last level dominates. Okay. This guy here will be done anyways. And it's large enough that effectively all of these other repetitions do not matter when you compare it to this. This already dominates. And the way to see this, and we're going to end with this note. So let me just show you very quickly. If you look at so this is like the time complexity of iterative deepening. I know we're going a little bit over time, but that's fine. We have to finish this so we can start a new subject next time. So here's the deal. It's pretty quick, actually. And it's an interesting observation you need to know in general about these kind of trees, which would be helpful more broadly. Look, iterative deepening will expand in the first iteration. That is when the level is 0. It's gonna expand b to the 0, b over b minus 1. Where did you get this term? We wrote this before, because that's the size of the tree. When it's L equals 1, it's gonna be b to the 1, b over b minus 1. This is the number of nodes in a tree up to that depth. If it is L equals 2, same thing, b square, b over b minus 1, and so on, okay? So when you get to the last level that you're gonna expand, it's gonna be d. So this is gonna be b to the d, b over b minus 1. Okay, now I'm gonna see a surprise now, a quantitative surprise. We're almost done, give me just a second here. We're gonna add these guys up. Now, if you add these guys up, you do it at home, but what you're gonna get is the following. You're gonna get b to the d and b over b minus 1 squared. Now, if you're looking at a tree, depth d, branching factor b, we already said that the number of nodes is b to the d over b minus 1. We did this derivation in the first hour, okay? That's. What happened here? With all of these repetitions, the only thing that happened is that I'm now having b to the d with b over b minus 1 squared. So the only difference or ratio or redundancy that I'm having is a factor of b over b minus 1. That's the only real difference between what depth first or breadth first will do, which is one pass over the whole tree, and versus this guy, which is going to be doing these redundant iterations. That's the only difference. Now look, when b equals 2, how much is that? That's just a factor of 2. I'm just doubling the time in a sense. And as this branching factor grows, right, the overhead becomes even less and less. So if b equals 3, you get talking about 1.5 times more. If b equals 10, it ends up being only 1.11, right? Your book has this example, which is, I don't know how the authors came up with these nice numbers, but they have a branching factor of 10, depth of 5. And if you count the number of nodes in a tree with these properties, you're going to get this number. And if you see how much iterative deepening will end up visiting with the repetitions and all of that, you're going to get this. Okay, I don't know how they made these numbers up. I hope they're correct, actually. Maybe someone can verify them. It looks too good to be true. But you get the point. All right. So, folks, this is pretty much what we need to say today. Let me get my camera on. we started with breadth first. It had some highlights. Then we did depth first. The highlights of breadth first were completeness and optimality. Then we went to depth first. The highlight was the space complexity, but it was not doing well on completeness and optimality. We had a temporary fix. This is the half strategy, which is limiting the depth. And we finally got to iterative deepening, our reward for the day. And it ended up being optimal, complete, time complexity similar to the other guys, space complexity is linear, is just fantastic. All right, so this pretty much closes the subject on uninformed search strategies or blind. Next time we're going to talk about an exciting set of search strategies which are informed or heuristic. They say, give me a little bit more information and I can really do better than these guys. And again, there will be really one main guy, which was actually a breakthrough in search strategies, used very common. So, folks, we're done for the day. Thank you very much. And again, sorry for the delay. And I will hang around for just a little bit more in case people have questions. But otherwise, I will see you on Tuesday. Thank you.